And to that end, we have AMD here. And Mark Papermaster is, do I see Mark? There he is. He's is coming up, and he's going to be sharing. He's going to be sharing with us. He's the CTO for AMD, and I don't know. I have come on up, Mark. I have you know, a widget building bent in me. I do sparks and bolts. I'm a mechanical electrical engineer, and I got to say, like, everything I build, Mark, has a piece of silicon in it these days. And I was even building a wind sensor the other day, and you know, we just went up and we spun up a little custom board, and we got a little tiny processor and stuck it onto that thing, yes, and a bunch of MEMS transducers, just because it was the right thing to do. And so I'm really excited to have you here to give us a view of your where you see where you see the market of custom and new silicon going, and all the cool things you're going to talk to us about.
Excellent. Thanks for having me. Appreciate it.
It's good to have you here.
All right. Well, I'm going to grab the clicker, and while that's coming up, I have to say I have the dubious honor of the placement being right before we break for you know, the reception. So I thought to myself, well, that's a challenge. But then I thought, it's a different challenge. I'm going to be optimistic. I am an optimistic person, so I'm going to say that the challenge is that we talk about the next, whatever, you know, 30, 45 minutes, and we look at where technology is going. We look at this inflection and what it means to you all. That's why you're here. You are enabling the whole creative elements across multiple industries. And so I'm going to take the challenges that we walk out of here and we're toasting to the opportunities in the industry. So that would be my hope. But I'll tell you, I really am very excited about this inflection point. And you've heard about it from the previous speaker. You've heard, you're dealing with it every day, the transition, the inflection that we're at. And it's an often overused word. I mean, we're in technology, so you're really always in a transition. There's no new news there. So why is this different? Well, I can say, I look at it from my perspective. I've been well over 30 years in the industry, you know, started in a mainframe era, you know, went through all the transition into microcomputing, PCs, mobile devices that were connected everywhere, connected at, you know, 100% of the time. And I've seen a lot of that transition. Each of them was major in its right. But what I'm seeing now as compute and visualization capabilities combined with machine learning takeoff, this is more momentous. It really will impact every industry that you are in. It will impact society as we learn how to really use this new technology in very productive ways. So it truly is a massive transition that's upon us, and it's a challenge to all of us as to how we deploy it. That's what I want to talk about. I'll give you a perspective, an AMD perspective, Mark Papermaster perspective, but I wanted to disperse some thought. Hopefully we have a little time for Q&A, or at least to be able to talk after the event. But let's first make sure that we're together on what it is that's the driver behind this transition. It's really a couple of fold of what's going on. You know, there is an explosion of data. I'll talk about that. We see it. You all are part of it. Look at those smart devices in front of each one of you. You are personally generating a massive amount of data, which if you were wondering about that before the last few weeks, and you know, if you watched a CEO of a very famous social media company testifying in Congress, you know that there is a massive amount of personal data that we're each creating, but it's much more than that. Sensors are now embedded everywhere, and the rate of that inclusion is going from everything in the home, your refrigerators, your doors. I've got my home fairly automated, to every aspect of actually products or the industrial factory floor. So the amount of data in almost every vertical you look at is exploding. And in addition to that, what you're seeing is the very way that we have to think about managing that data from both the computation and visualization side is changing. And then, of course, making that data useful needed a new approach. And the algorithms and machine intelligence have advanced dramatically in the last 5 years. And more than that, the ability for people outside of supercomputer centers to be able to use those algorithms has been made accessible. So these elements have come together. And what it means for the industry that you all come together, when you come together at COFAS, you're here for a common bent, a common passion that you have. And that's why I believe that the ability to enable content creation is coming to a fundamental shift in being able to truly bridge the physical and the modeling worlds. And that's what I want to talk about. We're just one piece at AMD of that food chain, and it's a very exciting confluence that has to come together to make this transition happen. And at COFAS, you bring those elements together. So let's talk about that explosion of data. Well, you know it. Again, we talked about it a moment ago, all the massive creation of that data. But you know, it's not just in the use cases that we think of day to day. I don't know if you've thought about how some of the industries are changing the very way that they're doing their base investments as they think about that, utilizing that data. Look at GE spending $1 billion last year, 2017, in data analytics and using the data that they pull together across the data, across their industries. Look at an example of Airbus. When they designed the A380, they put over 10,000 sensors on the wings. Why? Because they have the ability now to manage that data and fly much more efficiently, much more accurately. It's a massive plane. We'll see if it gets commercial success because it's trying to seat over 1,000 people on that plane. But guess what? The technology's there to do it, and you couldn't do it without pulling in this massive amount of data and having automated closed-loop control systems. So just an example of the importance of data and how it's being harnessed in some different ways. But when I look at it, and I look at that explosion of data, I am biased. I am coming at it from the standpoint of where I spent my career, and that is, well, how do you manage that data? What do you do with that data? And it is driving a massive increase in demand for both compute and visualization. From a visualization standpoint, fundamentally changing how we interface with computers as you're getting higher resolution displays, as augmented reality, virtual reality. It's truly a transition in the way that we'll be interfacing with computing going forward. But as I change how I interface with computing, that's great, but what changes the usefulness of that? Will it mean just that I have a better entertainment options? Will I have better gaming options? Well, that is one of the key markets. But if you can harness the data in both the cloud and how you bring it in real time, right at the factory floor, right at the generation of the source of that data, as you can start to harness it real time, it makes that data useful to you where you are, wherever you are. And that is where managing that data, putting the smart algorithms behind it, can really blend the advances across both compute and visualization and bring it together in a very powerful way. So we'll start just a minute on that first aspect, on the visualization. No surprise, you've seen this coming. But I'll have to say, I was actually at Apple in my career when we did the Retina display. And we were after changing the experience, but what I realized after is putting out the Retina display put sort of a challenge in the industry. It put out there for everyone at a consumer level to realize what a difference it makes when you get a much higher resolution, when you have a much better visual interface. And it really raised the bar, and it drove a faster advancement of display technologies. It started in mobile and then moved into a much more rapid pace across really every display technology. And that's what our expectation is now. We don't accept less. What happens now when you even look at not only a 480, what about even a 720p display? You are not happy. You're saying, who stuck me in the hotel room with this old technology display? Your bar is raised. You want a better visual interface. And the good news is, I see us on really an inexorable pace. I have at home, I was really excited this last year. I'm a bit of a geek. I'm into all this stuff. And finally, the price point of a 4K, 10-bit HDR OLED display, came out of the stratosphere and, got to still expensive, but, it was, in the realm of affordability, certainly for folks that are really appreciate and are willing to put more of their budget into technology. And I have to tell you, I'm thrilled with it because when you look at that kind of resolution and you look at the contrast ratio and you look at the wide color gamut you get, it's a different experience. The images pop out. I like it more than 3D. It really pops at you, and it's a great experience. And you look at now 8K coming up right on the heels. We actually have an 8K display at our AMD booth. I urge you to stop by. It's the next step. I mean, it's really, you're seeing now changes in display technology. It's still 2D, right? So you look at the 2D interface, but you're feeling depth. You're really seeing true coloration. And, it's very, very exciting, but we have a long way to go. If you look at that 8K display, right, you're looking at about, 4x of a 1080p HD display. What does it take to actually get to an immersive environment where it mimics what you see in the eye, right? What that takes is yet 64x from that original HD display. So there's a long way to go. I tell that to the engineers at AMD on our Radeon team all the time. We have no shortage of innovation on what we can do working with the display industry, but it really makes a difference as we drive this technology forward. It makes a difference for feeling more immersed on a 2D display, but think about the challenge when you go to a virtual reality, because now that display has to render at really 60 frames to 90 frames a second if you want to feel like you're in an immersive environment. The delay from the photon to eye, that lag has to be less than 10 milliseconds, so you actually need to become ill as you go through that VR experience. And the more and more resolution that you can put close into the eye, you need all those factors together to create a truly immersive environment. And I clearly see that happening. We're working with display vendors on that technology. We're working on how do we cut the cord and not have to have the cable that you have today if you want a high quality immersive VR or AR experience. But it's all moving very, very swiftly. And I tell you, it's a phenomenal innovation in this area. And you're going to just see very strong, I show a nonlinear slope as we seek that immersive experience on virtual and augmented reality. And the benefit of where you're in the front of the 2D display is it's going to get more and more lifelike. So tremendous advances, continuing advances on visualization. And what does it mean? It means that as you start to bring VR and AR to a really high quality experience, you're going to see more and more applications. I know when you look at the projections from, I'd say about 4 years ago, you'd have expected that today there would be a much higher install base of VR. Because that's, that if you looked at all the IDC, it would be there today. But it's not so, right? It doesn't mean it's not happening, it is happening. But you need both a quality experience and you need the applications that make sense of using that technology. There's a few of us geeks that get technology for technology's sake, but that's not the mass buying public. It has to be solving a problem. And although I personally expected back 4 years ago that it would be media and entertainment that would drive the bulk of that bow wave of adoption, it's actually not. It is commercial applications. Go look at Accenture. They've got scads of programmers creating industrial applications of VR for training, for sales experiences, for actually, right in I'll say the shop floors, right? And that's where you're seeing the initial adoption. But it is going to start moving across more verticals, and it will come to the mass experience when the App Store came for mobile phones and it became easy to develop applications, suddenly smartphones took off. It will be the same. Developers are working. It's got to be hardware and software working together to make it easier to get those into applications. That's what's going on. Just like you've seen all the library development helping video game creators develop more efficiently. Look at CAD and CAE. It's very modular software development. That has to come to VR and AR applications, and it is. And as you start getting an ease of implementation, you then start getting the killer apps. You get the hardware that has to progress equally with the software to get you this more seamless experience, bring the cost down, and we will indeed hit the knee of the curve, and you will see a broader adoption of this technology. I think it's very exciting. We remain very focused on this at AMD for sure. And then, of course, I talked about the kind of computational oomph that goes hand in hand with visualization. And, I think certainly at COFES, this is not news to anybody here, right? So you do need what I call lightning fast, both CPU and GPU. And it depends on the workload, and they're used interactively. And that's what we've been very excited about in AMD, is what we're kind of heads down, if you think about the last 5 years leading up to 2017, because we had to revamp our roadmap. We saw the trends that I just described to you, and we didn't have enough high performance in our CPU roadmap. So we started from scratch on a new design. We launched it last year. Started in our Ryzen, both commercial, on consumer, and then in commercial with Ryzen Pro, and then servers with EPYC. And we are bringing very, very high bandwidth, very, very deep memory to this aspect of the market. And then, of course, with our rendering with Radeon, we've been very focused, including adding solid-state drives, 2 terabytes of solid-state drive. And why do you need it? Well, you need this kind of computation because creators need to be able to handle vast amounts of data. Because creators, their bar has also gone up. Yes, they want better displays. Yes, they want more capability of the complexity of the models they can handle, but they want it real time. The design cycles are shortening. And so you have to bring a high-performance computation and visualization to enable a faster design cycle, a faster creation cycle. So I mentioned one example here is real-time ray tracing. Right? And you look at normal rasterization, it's already a fairly high computation activity. But when you add the real-time ray tracing and you have to create orthogonal to every point, you have to be calculating the light reflectivity, that you have to traverse its path, and you have to rasterize it. Right? It's adding significantly to the computational tax. But that's what creators want. And that's what they're going to get, right? Because that's what is going to drive the economics of their business forward. So that's another area we've been focused on. We did announce, at GDC, the Radeon Pro Render, where we're accelerating the capability for rendering. We're accelerating ray tracing, and yet we're doing it like we do most all of our development at AMD. We're doing it in an open source fashion. We've coded in OpenCL. It'll be moving to Vulkan soon. It's hardware agnostic because we believe these kind of capabilities are needed to move the whole industry forward. I think we just announced today the plugins for Mac. It can be plugged in. You can use this with different combination of vendors you may choose. So again, hardware and software really have to come together, and we need to be able to lift the industry. You'll see that as a consistent theme I have. To move the industry forward, we need more computation. We need hardware and software moving seamlessly, and we need to do it as an industry. We need to be able to really do that such that we can build off one another as we create content, because content drives adoption, and it drives the cost cycle down. So again, we were focused as a company on getting competition back in the industry. I described to you earlier about CPU. On GPU, we now have top to bottom, low end to high end, a very, very strong product line. Our Pro WX 9100 based on the Vega technology. We've got, right through the mid-range, leveraging our Polaris GPUs and drafting modeling down to the W4100. So it's very exciting for us at AMD to bring competition back and bring it back with the attitude we have. We are a company with an attitude, and it is that we are the scrappy underdog that wants to bring competition, collaboration, open source, and partnership to the approach in the industry. So that's what's behind the product line that we rolled out across Radeon Pro over the last year and a half. I'm going to shift gears a little bit. You were just talking about, and the previous speaker, about AI and machine intelligence. And I want to spend a few minutes on it because, as I said in my opening comment, it is incredibly impactful. And we already talked about this explosion of data. How you harness that data is critical to make it useful. And again, for the point I just made, even when I was talking about our visualization applications, same thing in machine intelligence. It's hardware and software working together seamlessly if you want to truly leverage your data to a productive end. So, when I want to make sure that we think about the elements that it takes to do that successfully in the same way. And to me, it's pretty simple of what's come together here is to fuel this opportunity to leverage machine intelligence. One, if you don't have data, you can't run training and learn the data and recognize patterns and make that data useful. So you have to have representative data. Well, check. I think we already talked about that, right? It's much easier now to gather that data given the lower cost and proliferation of sensors and data acquisition. Okay, well, fine. But do we have the algorithms to take advantage of this? Well, there's been a big change, right? I talked about it. Really started, think about AI. It's been around when you think about the perceptrons that were developed literally back, 50 years ago. This is not brand new technology. So why is this new that suddenly we have algorithms? It's new because the advent of how different convolutional neural nets are created and how the learning that's gone on so rapidly in the last 5 years with collaboration, right, across academia and industry to hone the algorithms based on the problem set. What matrix size do you need? How deep does your neural net need to be to actually learn this, sift through this massive amount of data and make it useful? Has dramatically changed the capability of the algorithms in the last 5 years to where now the accuracy, whether it be just pattern recognitions or anomaly recognition, is phenomenal. It goes beyond what we as humans are able to do. We can't sift through that data. And it goes beyond historical algorithms. I look at seismic industry. It's been a high-performance compute, a high-performance industry as far as you look back, because that's how you discover oil. The oil exploration has to examine the floor, look for where you have pools of oil reserves. And it had a fine algorithm called RTM. And When you look at the reverse time migration, the way this whole algorithm worked, it was very, very effective. But when the oil industry started applying these CNN and machine learning techniques, it surpassed the accuracy very rapidly. And it's displacing an age-old, tried and true standard algorithmic approach. Just one example of how the algorithms are really coming to bear now. And then ease of application development. That was another fundamental element is, it started with Torch, it started with Caffe, and then of course TensorFlow, CNTK. You see the proliferation of the frameworks. Why is this so easy, so important? It's not so easy, but it's so important, is you're starting to hide the complexity. So, you could always have written, the usage of incredible horsepower, teraflops of CPU and GPU in our national labs, as I mentioned earlier, it's been around for years. But it's been a very low-level coding to take advantage of it. These frameworks allow you to program at a C++ or a PyTorch level, high-level programming. Use that framework to call out the math libraries. Those math libraries are being extended now, but that concept has been around a long time. High-performance compute, HPC, has used these math libraries for years. But now it's easier to deploy. And so, that's the third key element. And then the fourth key element, it's where I spend most of my waking hours with the team at AMD, and that is that all only works if you don't have to be at the national lab to get the teraflops of high-performance compute. How about if we, drop this such that your workstations can have very, very significant teraflops? And that's what we and the industry have done, is we've been focused on bringing high-performance compute right into the workstations. So I won't spend a lot of time on this. I think most of you are familiar with that, but it's important to think about how machine learning is brought to a use case, an application. Because you've got the scads of data, and you're trying to make sense of it. You run training, which means you're iterating through that data. You're looking for patterns. You're running typically a convolutional neural net, but there's many other algorithmic techniques being developed based on that data and how to get the most accuracy. But you're having to iterate through in a forward propagation, and you have to have spent some time. You actually have to label that data. If you go to a lot of the machine learning startups, you'll see college interns sitting there, actually labeling data, whatever it is that they're trying to classify. You've got to tag that data, because as you're learning, you're going through and you're saying, well, how accurate was I as I forward propagated through and tried to make sense out of that massive data that I was examining? And what do you do in training? You have to loop back. You have to do a backward propagation, adjust the weights across your matrices. It's all linear algebra. I have urged my college-age son to please take linear algebra. And you have to adjust those weights, iterate through again, compare the accuracy again and again and again. It can take weeks on the highest performing racks at data centers with the highest performing CPU and GPU. But that's what it takes, massive teraflops to achieve this. And at CPU, GPUs, you'll have specialized devices, but they're limited to a specific algorithm. But you'll see ASICs, you'll see programmable gate arrays. So, it takes a tremendous amount of computing. Typically a GPU today, although you have these other techniques, but typically a GPU today to accomplish that training. Then you have your weights. Now you have those weights, you run inference. And that's, it's a forward propagation only. And you can come down to the simplest class of, Hey Siri on your phone to Alexa, and you can go to much more complex inference applications. And automotive, I'll talk about that in just a bit, is that example. And that type of inference application is coming right in to product lifecycle management, PLM applications, CAD and CAM and CAE design. Because if you can harness that data and bring it right into the content creator, think of how powerful that is if you could do that real time. And so that's what we're starting to see. We're starting to see new applications that can allow creators to create not only faster, but do things they couldn't have done without machine learning. Because if you can go through the world database of knowledge on an aspect you're trying to design and have that vast history influence how you're optimizing and how you're trying to create new applications, it has immense impact. It's really a fundamental change. I show examples across, of course, human-aided design. What about medicine? It's being used today to analyze X-rays and diagnostics. And, a doctor, you have a fine doctor, but they have the knowledge that they've been able to gain and, certainly extensive training, but it's limited to their personal experience and training they could accomplish. What about when you open that up to the mass database of diagnostics? You tag that data, you have known anomalies or differences you can look for. Think of what that does to the diagnostic accuracy. So there's a lot of fears about use cases of machine learning, but really you can go industry by industry, and it's no different than other technologies that have come. A lot of technologies can be used for ill purposes, or they can be used to push beyond what we ever thought imaginable. And that's what has me excited. When you look at the area that COFA's focused on, there's tremendous innovation going on. I'm probably talking to some of the experts in these areas, and you can even school me later on some of the barriers and challenges you're facing in this area. But I have to tell you, from being the guy designing the engines underneath, I find it phenomenally exciting because this is the kind of new design approaches we want to help spur on. You look at generative design, and what you're trying to do with generative design is really being able to change that creative process to leverage, just like the example I gave you of the radiologist that can leverage that vast history of prior diagnosis. Imagine if you're the designer, and when you're designing a new element, you can put parameters. What size do I want this? What are my constraints? What are the materials? What are the costs of this element I'm designing? And draw upon the database of all the materials that are at play, similar base designs. And you can draw on that in a generative, iterative process to within the parameters that you set to help that creative process and show new ideas and new approaches. That's what generative design is, and it's already getting some phenomenal success cases across many different design applications. Likewise, I'm thrilled with what I see going on in digital twins. I go back, again, I have to date myself. When I started in the industry, the first program I worked on was the space shuttle. We were working on the first space shuttle flight, STS-1, and we had a Singer Link simulator. It was, I don't even want to know what the cost of it was. It was massively expensive, and it was trying to mimic everything that the space shuttle pilot would go through. And I was on the team that we had the computers and the software behind it, and so we were working closely with them. But when it was, I'll say, a far approximation of what those astronauts really experienced when the shuttle took off and the real variables came in. Now, of course, they're trained to be able to handle those anomalies that may come up. But think about that when you can, in the design process, change to where the physical world is directly affecting your design. Imagine if, as you're looking at adjusting, let's say, a turbine design, you're feeding in one aspect you're designing, if the other aspects of the design are actually being fueled by real time by sensors on a real turbine. So you are designing in a digital twin, right? So you're adjusting elements where the rest of the system is being fed by the physical implementation of that design. By the way, the data that's pouring in is available to you to analyze and recognize anomalies and trends and patterns with machine learning techniques. And so you have changed the design experience to be real time, a true marriage of the modeling effort and the physical effort, and have it be influenced by the history, as you can run machine learning algorithms, again, to optimize, to help you optimize, to help you detect where there may be challenges that you have to address in your design process. Look at a turbine. They're finely tuned machines. You can't have any vibration. You can't have any sources of friction. I mean, the design complexity is phenomenal. And so it will fundamentally change aspects of design. And it will shrink the design cycle of this innovation, of this creation. So it's affecting many industries. You look at autonomous driving. It requires massive recognition of everything around it. Right? Level 4 is still driver assisted. The Nirvana is a level 5. But it's the only way that we're going to get there is that the software has to be incredibly robust. It will drive safety up significantly from what we are able to do as humans. I know you've read, like I have, the news reports, and it's tragic that in the testing process, I mean, there's been recent setbacks, and that needs to be dealt with, and policies need to protect the public and the learning process for sure. But the impact of PLM design approaches to be able to allow that software to adapt and to become more accurate in real life situations will hands down improve the safety for all of us in the driving experience. The data is already there, even with which are frankly rudimentary driver-assisted programs that are out there today compared to what it will be in 5+ years. The data is already there that safety is going up dramatically, right? So as a design community, bringing hardware and software together in the creation process, we accelerate entire areas such as autonomous driving. And it really is hardware and software coming together. It's going to be a huge growth rate. It's already running double digits. It's going to continue to run about a 20% compounded growth rate, really as far as IDC cares to project out at this point. And it fundamentally, you have to think about a car as an edge compute device. It's connected to the cloud, but it's going to have to be able to operate standalone, right, when you're areas where you don't have that connectivity. And it has to be real-time processing this massive amount of data that its sensors are collecting. And so it really represents what you're going to see more and more. You're seeing this on the factory floor. You're seeing this anywhere there's a massive amount of data that comes in. It has to be analyzed, typically inference, but sometimes hybrid inference and training on that data to react as elements change beyond that original data set that you had as you ran your training. And so computing, high-performance computing, is moving from the cloud to the workstations to the edge nodes, which are embedded in the verticals, and of course the traditional client, the endpoint, where we interface with computing, whether that be a flat screen or a virtual or augmented experience. And of course, this is an area that we're focused as well. We just took our high-end Vega class graphics. We optimized it for high-performance compute. We added deep learning ops, so it can even accelerate deep learning, and really made sure it still supported all of our virtualization, all of our capabilities. So it's not just for automotive, it's for broadly in high-performance computing. But I bring it in at this point because it's an example of literally the kind of class of compute you need for these new applications. This is in the cutting edge 7 nanometer, and we're excited about this next generation design, and it'll be sampling the second half of this year. So again, I talked earlier about this, so I won't spend much time on this, but it is hardware, it is software, it's the applications all coming together, the whole tool chain. It is happening, it's there. We are going about it differently than our competition. We're enabling it in the areas that we focus. So you have, as I said earlier, the end applications that ride on those frameworks being the TensorFlows and the rest of the frameworks out in the industry. But the underlying infrastructure has typically been proprietary. And that's really the change that AMD is doing. We're not trying to bring competition only back in hardware, but in the full enablement. And so we have enabled and announced this year a production level machine learning stack that is open source. We put it out there on GitHub. You can go to gpuopen.com and you'll be pointed to the source of our programming language across our interface, across our portability, across our communication libraries, really, and including those detailed math libraries, which will then optimize the execution. So we do have a full open architecture stack for use on our Radeon GPUs for machine learning applications. So look, I want to wrap this up by really challenging you. So we're lucky, right? We're here at this confluence where the type of high-performance compute capability has come together with a software and algorithm enablement with beautiful displays, both 2D and that all-encompassing virtual reality and overlay and augmented reality. We're lucky to have this opportunity. And when you look at this COFES conference and it looks at the kind of talent that's been brought together here, I do hope it spurs that discussion of how can the industry come together and accelerate design and accelerate innovation. Again, I've been at this many, many years. I truly believe that in your entire career, you'll have a chance to have a greater impact on designs, on products. Products impact people. You have a greater opportunity now than ever to impact the world around us. With that, thank you very much.